So I am actually recording this session as well for the people that are not able to join and want to watch it later. So I am actually connected with two devices, so I want to check whether it works or not. And what did I do? So, okay. Where can I give access to everybody like this? Yeah. Okay. So can you also write something like drawing something or writing a formula? Okay, that's good. You are good painters. Okay, so what else I should. So the point is like this, that I am going sometimes to write something, sometimes you should write something, and sometimes I share my desktop. It's gonna be like this. So so everything is going okay with you? Like you have any question or something? You know that the session tomorrow will be held on by Professor Pipa, and that's it. If you have questions regarding your exams or uh, about the evaluation process or about the lectures, you can ask him. And the fourth lecture is also have been uploaded, and you can also find it now. So is there anything you want to say, or we can start? Can I ideas for final project? Uh for final project papers. Well, we can talk about these. I also have some papers in my mind. I am. We are working on some papers as well, right? For instance, we worked on. We didn't work actually. We read part of Sturget's paper about love affairs, and this time, if we have time, we will talk also about the Izhikevich neuron model, which is another paper, and maybe these things are like inspiring for you. However, about new papers, I will also think about it, and I inform you. Yeah. Okay. You can also ask about this of Professor Pipo as well, right? So, uh, how can I clean all of these things that you maybe here, maybe here? Okay. Uh, well, the thing that is happening is that I am going to be connected with two devices, and that's the point. So let me actually try. Okay, so probably it seems that actually I can just access to part of it, like, so you have my screen now, right? Okay, okay. So let's going and start with this is because of you have it now, right? Okay, so we're going to talk about fixed points, and in this fixed point perspective, we know that here but you don't have my mouse, right? Or you have? No, you have, I think, but with some delay. Okay, so this x dot, we are going to draw the, like we have the form x dot is equal to f of x, and when we have these kinds of equations, we say if we draw x dot with respect to x and whatever that it is, you will see that the crossing points, like these circles, like these points, which some of them are fulfilled and some of them are open, we call them fixed points. Why? Because x dot is equal to 0. But the definition of x star, which is x of fixed point, is the place that f of x star is equal to 0. It means that x dot is equal to 0. It means that a kind of like physically you can say actually that velocity is 0, right? So about the stability, we simply just say that if f prime, like the derivative of f at the point of x star, which is the fixed point, if it is negative, then it is stable. If it is positive, then it is unstable. What it means that here, for instance, in this diagram, in this graph, you can see that here it is positive, and the state of the system, what it means that x dot is positive, right? It means that in this x, the velocity is increasing. Therefore, x is increasing. Therefore, it is going to attract to this point. And here, it is negative. Therefore, it is going to decrease. X is going to decrease because the velocity is negative. Therefore, it is going again to absorb why it happens like this. Okay, sorry. So therefore again you will see that it is going to absorb to this point. Therefore it is an stable fixed point, because actually if you draw a line over here, maybe I can do it here even. I try. So in general, I am trying to actually I shared my desktop like on my laptop, and I am using like an AirDrop thing, so you will see a kind of delays, and sorry for this. So here you will see that this slope of x dot is something negative, and here you will see that the slope of x dot is something positive. So this is actually the meaning of f prime, which is negative, and f prime, which is positive, at the x star, which are the fixed points. And if it is positive, it is stable, unstable, and vice versa. Okay, so we want to talk about linearization. So in the linearization part, you can say, so let me tell you that we have a kind of curve here, like take Earth for instance, and on Earth you want to build the house or whatever. Therefore you try to put it like in general a curve which is coming from a very great radius. In smaller scales you can look at it like linear line, right? So this is actually the concept behind all of those uh, differential equation, not differential equations actually, the ability of defining derivative of something, so of a function. Therefore you have something like, you have a very small thing like here, like take like epsilon, which is epsilon is very 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 small, for instance, in compared to 1, but it is positive. Therefore you can say that I am able to define something like slope. So that's the point. So with this linearization idea in general, you say we have something like Taylor series, and in this Taylor series we have a function like f, which is kind of arbitrary function, but it is very complicated. It can be a nonlinear form like x2, like x squared, like x cube, or these kinds of terms that are making the equation nonlinear. And then you will make it as a polynomial, like 1 plus x2 plus x3. For instance, if you have some function like sine of x or exponential of x or whatever, you can bring polynomial thing out of Taylor series of it. So this is the thing about Taylor series, and we will refer back to this. But in general, that fixed point, it has some neighborhood, and in that neighborhood we are going to deal with a concept like linearization. Therefore we say if we have this x, which is equal to x star plus a little deviation, like a very small epsilon. Here, for instance, you can say that if it is x dot, you are talking about a very close neighborhood of this point. Then you can say that actually around, like near to that fixed point, x of t is equal to x star, which is your fixed point, plus epsilon. And you have two things. You have x dot. What is x dot? X dot will be the derivative of this, right? Therefore, this x star is nothing changeable, and this is going to be 0, and the only part which is remained is epsilon, which you call it like epsilon dot. The other thing is that x dot, on the other hand, you have it like this formula, x dot is equal to f of x, right? And this f of x is here, by this definition, it is f of x star plus epsilon. And if you do the Taylor series, what is the Taylor series? Taylor series is saying that around a point like x star, you can expand the very complicated nonlinear function like f of x, like equal to f of that point, like x star, plus the deviation that you are, it makes you very close to that point, times the first derivative of it, plus some other like epsilon squared times f double prime of x star and stuff. So if this f prime of x f prime of x star is not, sorry, this is wrong here. I wrote something wrong here. This is if if it is not 0, then it is neglectable, so we can forget about the rest. And so this f and also f prime, both of them are functions, but because you have just a point like x star, here you will say that this is going to be a number instead of a function, and we call it like something like r, because then we are going to refer back to that. So we just need this name here. So you have this 1 and you have this 2. Therefore, with the combination of both of them, you say that this x dot, which is epsilon dot, is equal to this number 2, which is actually, this one is 0, right? So because x dot, this is the definition of fixed point. So we forget about this and we forget about the rest, and we just have this part. We just have this epsilon f prime of x star, which is equal to, so we call that like r, and this is going to be equal like r times epsilon. And this is this epsilon, let me actually write it here. This epsilon dot over here, this is equal to d over dt of epsilon, right? Therefore, you have a kind of, you have d over dt of epsilon equal to r epsilon, right? This is a differential equation, right? A very simple linear one. And if you do, it is also separable. Therefore, you say like d epsilon over epsilon is equal to r dt, right? Therefore, you take the antiderivative of both sides and put the ln so just let me check how many of you can actually follow this. Does it need to solve it now? Or let me ask you whether any of you can actually solve it. Okay, I saw your message now. And can anybody actually write here the solution of this? I mean, maybe I should do this and let you to write. So the point is like something like this, right? D over dt of epsilon is equal to r epsilon. This is a very simple nonlinear equation. So, and this is also, we know that this is we also know that this is a separable equation. What does it mean? It means that you can write like, if we have like d over dt of something like you can write it like if it is like f, then you are actually able to write it like g of x times h of, sorry for this, times h of y, if you have just one thing. So forget about this. It's awful. It's awful. Maybe I can write it here. here you have this, right? Here you have this, and you say that the antiderivative of the epsilon over epsilon is equal to the antiderivative of r dt. Therefore, you say that ln of epsilon is equal to rt, right? Therefore, you say that I put something like exponential here, like e to the power of ln of epsilon is equal to e to the power of rt. Therefore, you say epsilon, this ln and e will meet each other.
Excuse me, we cannot see what you are writing, or at least I cannot see that.
I think yes, you are right, because I am writing on the other device, and it is just will emerge. Sorry for this. Yes, now I think you should have it.
Yes.
So this is like this, that we have d over dt, and we bring this dt on the other side, and we take this epsilon on the other side, and after that we have this, and then we take the antiderivative of it, or to some extent integral of it, and the integral of dx over x is equal to ln of x. This is the thing. So sorry. And also the antiderivative of r dt, because r is not a function of t. Therefore, r will come out of antiderivative of integral without any change times t. So ln of epsilon is equal to rt. Therefore, you put the exponential function to both sides, and e to the power ln of epsilon is equal to e to the power of rt. And exponential function and ln function, they are like they are cancel each other out, and then you will have epsilon is equal to e to the power rt, and this is just a constant, like epsilon naught times e to the power rt. So this is the very important concept actually here, because we had this exponential growth and exponential decay. If you go back to the videos, I think the fourth one, and if you see that r is positive, then you have growth, and if it is negative, then it is going to be like but with a very fast, because it is exponential, with a very fast velocity, it is going to be decreased and like decay. So this is the important thing about this r, that it brings you this concept, and that's it. So now we have this, right? We have this situation that if f prime of x star is not equal to 0, then we can do this. But what if it is equal to 0? In this case, you do not have any information taking out of linearization. I mean, you can also go through, because this is going to be 0, and you can go through these neglectable terms like f double prime and stuff, but it's just going to be harder and harder. Therefore, we say that instead of all of these things, we use graphical approach instead of analytical one. So so for instance here, maybe I again try here to write, and maybe maybe it takes a bit time. And if I just want to say like x dot is equal to f of x is equal to 0 to find the fixed point, then your x star is equal to 0. You can also say that what is the f prime of x? This is going to be 2x, which again here in x star it is going to be 0. So you have this and you have this and you have this and you have this. So I hope it came out.
Are you supposed to see something again?
I didn't hear you. May you say it again?
Did you just draw something? Like we don't see anything yet.
But now probably you can, right?
Yes.
Okay. So the point is here the point is that instead of solving those things analytically, which we can see that here x star is equal to 0 and also f prime is also equal to 0, therefore we say that in this x dot equal to x square, if we draw this, then we see that it is going to actually here it is going to cross this, and we want to talk about its this is the fixed point, right? X star is our fixed point, but we want to know whether it is stable or not. So we say that here it is positive, and like the both sides it is positive, and here you can also therefore you have some ideas. You don't know actually whether it is stable or unstable, right? So what will happen to this, or what will happen to this, or what will happen to this, or what will happen to this? So I wait for this to come up. So the rest is, all of them is ready, and this is the last one that has this problem, I think. So I'm interested to know your idea about this. If you can actually draw something. Okay.
Sorry for me, the connection was broken for a second. Could you repeat what we're supposed to do?
Yes, of course. I mean, here we have x dot is equal to x2, and what is x dot? X dot is always positive, right? And here x dot is always negative, right? So can you find the fixed points here? Like, what is the fixed point, you think?
When x is equal to 0, as you've already drawn?
Yes, exactly, yeah. X star is equal to 0, right? But the point is that yeah, tell me.
In the first example, so where x dot is x squared, I would say
it's a semi-stable fixed point, like from the left it's stable and from the right it's not stable, because the arrows always go to the right because it's positive. Yeah, the function is
Absolutely, absolutely. Yeah, this is the point actually, that you completely, you said it rightly. So this is we call it like half a stable fixed point. That's all it means. So about the rest also, about the rest, this is the third one is going to be stable, and the fourth one is going to be unstable, and we do not have any information out of analytics, but just as you could see or saw the power of visualization here, you can see that this half a stable thing is just emerging here, and you have the idea about it. And but it's an interesting thing to see that whether how can you actually what is there any meaning in this half a stable thing. The answer is yes, and the answer is that this is actually the point about bifurcation in 1D system. So in bifurcation we have a parameter that if we change the parameter, like in this Hodgkin-Huxley model, we change the current, right? If we change the parameter, then qualitative structure of the vector field. What does vector field here mean? Vector field here means that around this fixed point, you will see that there is a tendency, you can actually exactly define vector field with the slope, like the change, like the derivative of those functions around that point. And you've seen vector fields like in p-plane and stuff, right? So if the qualitative structure of the vector field changed dramatically, or the whole system changed dramatically, then we will see bifurcation. So this means that a fixed point is going to be created or destroyed, or their stabilities are going to be changed. So I mean, if you remember in Hodgkin-Huxley, all of them were converging to a point, and after that, that fixed point just destroyed, and a new kind of trajectory for the whole system emerged, and we saw a kind of limit cycle, which was the definition of a spiking. So the fixed point has been destroyed, or if it is created, or the stability of it is going to be changed, then we call it bifurcation. So we have in 2D, in 1D, like one-dimensional, we have three important types of bifurcations, with which we just talk about one of them now, and I will talk about the rest next session. But the saddle node bifurcation is the basic mechanism for creation or destruction of fixed point, which I should draw something here, and I will try to do that. Maybe you can do it sooner than me, but I try to do it fast. So we have this equation like x dot is equal to r plus x2. This is the basic form of saddle node bifurcation. If we want to have like r minus and r0 and r positive, then we have three types of diagrams, right? So I draw it, but I should wait a bit for
Yeah, we can see it now.
okay. So in the first one, you can see that actually we have two fixed points, and by increasing r, so I am going to increase r. What does r here means? It means something like, if you remember in Hodgkin-Huxley model, we had something like CV dot is equal to some terms like plus r I. So that I here is like R. So if we inject the current, for instance, or we change a control parameter of our system, then all of them are going to be changed. So by this, by increasing the R, you will see that these two fixed points is going to collide, and half stable, as one of you rightly said, going to be constructed, and the rest for R positive, then you don't have any kind of fixed point. So this moment, we call this moment saddle node bifurcation, which, like, this is a very basic example of this. X dot is equal to R plus X2. So if we want to draw the bifurcation diagram, we say that we want to find these x stars vs r as the control parameter and x star as our fixed points. So for finding fixed point, again we say x dot is equal to 0, therefore r plus x star to the power 2 is equal to 0, and we can find the plus minus of, I think it should be, yes, this is wrong here, this is minus r. So if we again want to draw x with respect to r, then you have something like this, or maybe so it's something like this, right? If we have something like y and x, and if I have x is equal to y2, then the point is something like this, and it is going to be emerged very soon. You will see it. But this is the thing, that by, like, if r is negative, then you have these are the x points. By increasing the r, you can see that the x points are changing, but all of them are stable. And here you can see that by for positive r's, you do not have any kind of fixed point, and for negative r, but the other part of it, like here you can see that it is going to be unstable fixed points. So you have a family, like a bunch of positive fixed points here, stable ones, and also unstable ones, and at r equal to 0, then you see that actually everything is changing, the stability is changing. This is the moment that half a stable thing is emerging. So this is the saddle node bifurcation, and this is what we call bifurcation diagram, x star vs r. These are the x stars, and this is the x for drawing this. So this is another example. If you have any question, you can ask, right? So here we have another example. These are very important examples, and these are some parts of our practice sheets, and this is why I am covering this, right? So x star is equal to r plus x minus ln of 1 plus x. If you want to again solve it analytically, you cannot. Therefore, you have to find again an approach like graphical one, which for finding the fixed point, you say that x dot is equal to 0, therefore here it is equal to 0, then you take this ln to the other side, therefore r plus x star is equal to ln of 1 plus x star. So far so good? Okay, I imagine that you did. Okay. So here, this line is ln of 1 plus x. This is, maybe I can, so in general, ln of x is something like, this. This is ln of x. But here, because we have 1 plus x, therefore it's going to be changed like through like the origin. It will cross the origin in this sense. And so 1 plus x, this is maybe, yeah, I think now it's better to see. So this one is r plus x, and this one is ln of 1 plus x. And if you decrease the r, again you can see that by changing r you can see something else, right? By decreasing r you can see that it is going to be like a tangent of like touching ln of 1 plus x, and then it will cross it to 2 points. Therefore you have no points here, then you have one, you don't have any intersection here, you have one intersection, and then you have two intersections. So this point again, which everything is going to be changed, we call it again bifurcation, the saddle node bifurcation, and we can see that this is the tangent intersection. What does tangent mean? It means that it is exactly equal to the slope of ln function. Therefore, the derivative of r plus x should be equal to the derivative of ln 1 plus x, right? So we have two things here. For these kinds of, for this one we didn't need, right? For this one we could find just by fixed points. But here it's harder, and we check two things: fixed points as well as the derivative of the functions. They should both equal to each other because of this tangent intersection. And this is very simple, right? The d over dx of this function, you can forget about r because it's constant and just x will remain, and d over dx of ln of 1 plus x. So this is going to be 1 over 1 plus x. And again here you can see that x star is equal to 0. This is how you can actually find x star. So this is our fixed point. So we found the fixed point, and now we want to find the control parameter, which is r. What is r? Here we say that again this at the fixed point r plus x star is equal to ln of 1 plus x star. X star is 0 as we found. Therefore, r is equal to ln of 1. What is ln of 1? Here we draw it, right? Ln of 1 is 0. What does ln of 1 mean? It means that e to the power something should be equal to 1. Therefore, e to the power 0 is equal to 1. Therefore, r is equal to 0, and we just call it r critical. The critical point that bifurcation is happening. And this is Again this happened. Okay. So near bifurcation at x and r equal to 0 and 0, you can have this function, which again you can say that x is 0 because of the x star, and x dot actually will be equal to r, right, mathematically. On the other hand, you have this function like ln of 1 plus x, which is equal by that Taylor theory, you can say x minus x2. Therefore, you can exactly write this like this: x dot is equal to r plus x, and you put the expansion, the Taylor expansion here, and these x are canceling each other out, and you already neglected the rest. Therefore, x dot is equal to r plus x2 over 2, and you can forget about this 2, and this is the normal form that we have about saddle node bifurcation. So
one question.
Yes, yeah.
This Taylor expansion, do we really have to understand it and to be able to solve it ourselves? Because in my curriculum so far, I didn't get to know it.
Well, understanding it is, I think, is not that much complicated. You don't need actually. You can exactly like maybe I'm just finding for some room to write something. Like you can maybe under bifurcation part here. Yes. So you can say something like f of x, like if you have something like cosine of x, f of x is equal to cosine of x. So this is the cosine of x, right? You will see it very soon. And you say that it is very close to this minus x2 . Therefore, you can write it like f of x plus f prime of x over 2 factorials plus something. So I mean, it's gonna emerge very soon. Okay, so you can see this this yellow one, right? So you see that actually here this yellow one is very close to, it's very similar to cosine of x. Therefore, you have some ideas that how to connect some function to some polynomial sequences, equations. So you can write it like a function of x plus a function of x2 plus a function of x3 plus a function of x4 and so on. But you don't need to actually do very you can there is this in Forum you can find a short video about Taylor series, and I can just tell you this, that you don't need to get any very like provable mathematical thing. You don't need that. You can just say that I am going to linearize this, and I have a function, and I am going to seek for the value of that function at a point, and at that point I just need to take the first derivative of it, and that's it. Just the first derivative of it. The first one is like f of x is equal to 0, therefore this f prime of x is the thing that you are seeking for. You don't need to understand the very basic and deep thing about it. Yeah.
Thank you. And I will look at the video that you mentioned.
Yes. That's very helpful because it's very beautiful as well. Uh, yes. Okay. So you have questions, or we can go on to some other things. Just for understanding this idea, like in the second assignment, we have something like a definition like potential. And potential is something like this. You can say it is all coming from physics, right? So you can say that here, for instance, you have a function like f of x. So, like in real world, you have f is equal to ma. What is ma? It is like mass and acceleration, right? And what is F? F is the force. So force is equal to mass times acceleration. So what is M? What is mass? Mass is equal to F over A. So it means that mass is a kind of thing that doesn't let the force for bringing the acceleration. M is equal to F over A, right? So conceptually, mass is something that the system, like a body, like a particle, will remain to stay, and you should give a force to that for having for it to has acceleration. So how can you define something like energy? You say that energy is equal to integral of these are not important, like just conceptually. So energy is equal to integral of force. Like if there is a force from a position to another position.
One question.
Yes.
What are we supposed to see? Are you writing anything, or are we only supposed to see the assignment 2 solutions?
Just the assignment 2, because I am actually reading this, right?
Good. Yes.
Yes. I'm saying that this is f of x. F of x, you can take it like force, and x or dx, you can take it like position, and the combination of them, like the multiplication of them, has the value like the concept of energy, which we call it, like for instance here, potential. So you can say, instead of this f, you can say like v, because here you have f of x is equal to minus dv over dx, and if you again take the x to the left side and take the derivative, here you will have just v, and here v is equal to minus integral of f times dx. So if you do this integral, and with this system like x dot is equal to minus x, you will see that the antiderivative of it, like minus x dx, is going to be x2. So why it matters? It matters because we just we can have this intuition that if you just have a ball right here, if you have a ball, this ball is going to absorb to this point. Why? Because the system is going to decrease its energy. All of these ideas, like even in neural network or like gradient descent ideas, all of these things is coming from the idea that the system is going to minimize its potential energy. It's going to it is going to reach the equilibrium state. This is why you can say that here, for instance, you can imagine a ball, and this, if you just leave this ball over here, this ball will just absorb to this point. And if your system is x dot is equal to minus x, then you have this. You can also say this about x dot is equal to x minus x cubed, and again you can take this integral, and by solving this integral you can see this. And again, by plotting this, you have this. And what is these points? You basically, I think now all of you know that this is an unstable fixed point, and these two are stable fixed points, which the bifurcation that leads to this situation is another type of bifurcation, which we will talk about it. So about linearization, I don't go into it now. However, if I just want to say something here, where was this? No. Okay, I cannot find it here. By the way, okay, let's continue about the logistic function. I can say it like this about logistic function. I said something like mistakenly. I said x double dot, and I didn't mean x double dot in the previous session. It was a slope of x dot. So that was all. So okay, let's if you have any question, you can ask. Otherwise, we can go through this. So we have a model named Izhikevich model. So we talked about Hodgkin-Huxley model, and we saw that those qualitative things matters. Therefore, somebody named Izhikevich just came and said that a model, he presented actually a model which is like Hodgkin-Huxley. It can be biologically plausible as well as computationally efficient. It should be efficient. So he introduced something, right? So if you go to the lab and you see the actual neurons, you will see different types of behaviors. You will see, for instance, this regular spiking, like it is just always just spiking with no difference between them. Or you will see, for instance, intrinsically bursting, that you will see several spikes in the beginning and then some spikes. Or you can see fast spiking, that's like by time you have a lot of spikes, and the model can actually generate all of them. So the model is like this. Actually, Professor Pipa covered this in his lecture, but I am also going to show some MATLAB simulations. So here you have V prime, which here it is something like dimensionless variable, but it is going to be to represent the voltage, the membrane potential of the cell. So I is the current, and this is just a model, right? He just took it from his pocket maybe, or whatever. So with this model, he actually said something like U. What is U? He called it like a recovery variable, which this U is going to actually represent if I can find it here. Yeah, V represents the membrane potential, and U represent membrane recovery variable, which is again about the activation of potassium and inactivation of the gates of Na and stuff. So if you, it's something like imaginary kind of, but it exactly fits the real, actual neurons. So by the by this condition, like if the voltage is bigger than 30 millivolt, then we say that we have something like C, which is another constant. A and B is also another constant. And if it is more than 30 millivolts, V is going to be C and U is going to be U plus D. So you have here, you have two equations and four parameters. Four, I mean coefficient. You have also I as well, but I is something that you can see it like in lab. So you don't need to define it here. However, with this U prime is equal to A times B times V minus U, with this A, B, and C and D, you can have any kind of neurons that you need for. So the parameter A is going to describe the time scale of the recovery variable U, which again it is kind of imaginary, but you can look at it like that tau of M or that tau of H that we were talking about. And also about the parameter B, which is the sensitivity of it. It is again something like made up, and by different choices of this B, you can have different types of bifurcations, which we will talk about later. And with the parameter C, also you can have the reset value that mostly we say 65 millivolts, and as well as for the parameter D, you can also another variable that makes the U actually to be reset. And you can have all of these neuron models like regular spiking, intrinsic spiking, chattering neurons that you can see a lot of spikings like here, fast spiking. I'm not familiar that much with these things like thalamocortical spiking or thalamocortical TC. About these resonators, it is also very interesting, right? Because we have integration and resonator, but we will talk about these things later. So that was all. V prime is equal to this, U prime is equal to this, V is equal to this, and this. You can ask your question, and after that, I go to the MATLAB thing. Yes, please ask your question. You had a question.
So is fast spiking the same as tonic spiking? Because in the lecture it was referred to as tonic spiking and the graph was more or less the same.
I don't think so. I don't quite remember. I can't give you an accurate answer, but I don't think so because the spiking that we had, I think it was like regular spiking, and it's interesting to see that these first spikings are different from the rest. So I think it was regular spiking and not fast spiking, because fast spiking is all of them are same and very close. Okay. So I mean, by these parameters of A and B and C and D, you can have different types of choices, which is computationally very cheap. So in the MATLAB situation, in the MATLAB So I am going to use a code here, and I upload this in the Froom, and you can also work with that as well. Okay. Okay, so you have my thing, right? My screen. So
Yes.
okay. So this is again our face portrait, and these are the null clients. They had two null clients. Because of this model, we have v prime is equal to this, u prime is equal to this, and with the change of these v's, you can see the moments that v prime is equal to 0 and u prime is equal to 0, and this is actually the important thing is about this I, right? Here, for instance, about these situations, you can change, you can choose over here, like A, B, C, D, and all of them are different types of neurons that we were talking about, like regular spiking, intrinsically bursting, fasting, and stuff. So if I, for instance, if I take the first one, I have these parameters. If I have the second one, I have these parameters, and you saw a kind of change over here as well. If I take the third one and the rest, you can see completely different variables. So, for instance, about this first one, this red dot is the state of my system, which is trapped kind of here. If I do this current, if I give the current to this, the null client is going up. This is an important thing, you see. If I inject the current, the null client will come up, will go up. So then the state of your system is completely different, and it is going to be absorbed in some regions, or it is going to kind of spiking in some regions. So I show this threshold. This red line is going to be the threshold. It is not still shown. Why? So I think my computer is not working that much good, by the way. So so if I inject again current to something else, like 20 for instance, then you see that again the null client will increase. So by the null clients you change actually everything, and the state of the system here, it is going to exactly come and reset on this green dashed line, which is going to be governed by these conditions here in Izhikevich model. So that's it. You can I don't know. I can't say, I can't talk like 1 hour maybe by this. For instance, by changing this B instead of positive, if it is negative, then you have another types of neuron. You have like excitatory, inhibitory things, and you can have everything. We should talk about it in detail, and you can also work on it. Yeah, I think I'm finished in this sense, but we should talk about this in detail. So, what is your idea about it? I mean, do you have any question or something? Because I am going to actually share the code on Froom to you, and you can you can work with that. Maybe I can do it now instead. So
Well, first, thank you for your presentation.
you're welcome.
About those different spiking um, things, I'm not really into neurobiology at all, so I can't really, like, I don't really have the intuition for it or why it's so fascinating. I just see, okay, there are different types of spiking, but I don't quite know how it connects to the bigger picture of cognition. But anyway, it's interesting that one can play around with it.
I see. I see. Well, uh, we will talk about it. I mean, this is part of our, like I think section 7 is like bursting neurons, and the point is, for instance, take something like adaptation. Adaptation is something very interesting in the whole evolution system, right? The system is going to be adapted. So in this adaptation, the way that neuron is going to, for instance, you inject a current, and by injecting that current, your neuron is going to uh, like the time difference between the spikings will be different. The neuron is going to be adapted to that. So first you will have, for instance, some bursting, and then you will have an increase in the time of spiking. So this is how you can actually talk about adaptation. For instance, you can consider a concept like adaptation, and I understand that like or like you can say, for instance, like chattering neuron. One of the examples that is important. You can enter like in a coffee shop, and you will just listen to some noisy things, right? You can say that there is no information here. You cannot recognize anything. But if you just going to look at a very locally at the table, you see that even some whisperings between the people, it's a meaningful thing. So this is why actually its name is kind of chattering neuron, because you can actually seek for some locally meaningful concepts, and some other like, but in general you are facing some noisy system. So I mean, there are a lot of pictures here, and if you do not understand this yet, it's my fault, because I still didn't cover that. And I mean, in general, if you are not interested in some kinds of scientific approach or whatever, it is not your fault. It is your teacher's fault, right? Or tutor fault. Yeah, I mean, yeah, but I understand your concern, and I will try to cover these things as well, to understand that what this means actually, what that means actually, and we have these things because, for instance, we have some important things, concepts like class 1 and class 2 neurons, and for defining those class 1s and class 2, which has very certain behaviors, with, for instance, with frequency and stuff. And those things are actually kind of full of meaning, like you by this categorizing and this classification you have different types of meaningful neurons. So I try to cover that as well, but we have to, right? This is part of our work. Yeah, I mean, I'm just going to share this MATLAB code with you, and we will talk about these models of neurons. Yeah. So I am also still available for that question or whatever. Well, anyway, I will do it later. I mean, after this session. So no question. Tomorrow you will be available, right? Because I mean, Professor Pipa will present tomorrow, and he will be available. You can ask your questions. I mean, maybe I already emailed the students, but if you think that this is a need, you can tell your friends as well. So tomorrow about these things that you are interested in, like uh, whatever scientifically or about the organizational issues or about the paperwork based things or something like that, yeah, you can ask tomorrow. uh, I am, well, I am seeing a question, and about this question I don't know actually. I am not sure, but if it is not uploaded, then that's it. But maybe, yeah, because I didn't check that. It just came out like 2 hours ago, kind of. I didn't check that. Yeah, you're welcome. Okay, so Anika messaged that it's kind of all the thing that you need for tomorrow. Okay, so to everything, I think, I hope everything is good, but I mean, if you have some question, don't wait until like next week, this moment. You can ask your question, right? I will try to be available during the week as well. let me see about this. So probably the next one will also come up. It is, it is not written like part one or part two, so probably this is the old, as far as I can understand. Uh-huh. Okay, so I'm afraid I should go and have a great day. Have a great night. Bye. Bye. Bye.